Welcome to the second lecture of this course Transportation Network Analysis. So, in the last class we were discussing about various optimization formulations and we had ended up with the optimization formulation of the shortest path problem. So, let us continue with that. We had looked at 4 cases where a node in this given network can lie in. So, the first case that we had looked was whether a node J is not part of the shortest path that is finally selected. Then the second case was when the node J is path of the shortest path that is selected, but it is neither the origin and or the destination node. And then we had the cases 3 and 4 where either this node J was the origin or it was a destination. So, one way to combine these cases is to look at these differences here. So, we have this summation XA where the summation is going over all of the outgoing links of node J minus summation XA where this summation is going over all of the incoming links of node J. So, for cases 1 and 2 this difference will be 0, that is because for case 1, since node J is not lying in the shortest path, therefore there is no outgoing link for which XA is equal to 1, and therefore the first summation in the left will be equal to 0. Similarly, the second summation here will also be 0 because there is no incoming link for node J for which XA is equal to 1. Similarly, for case 2, this first summation will be equal to 1 because there is exactly one link which is outgoing from node J and for which XA is equal to 1. And similarly, the value of the second summation will also be equal to 1 as there is exactly one incoming link for node J that has x equal to 1, and therefore 1 minus 1 will be equal to 0. Then for case 3, this difference will be equal to 1, that is because for the origin node there will be exactly one outgoing link for which XA will be equal to 1, therefore the summation on the left will be having value equal to 1, whereas the summation on the right side will be having value equal to 0 because there will be no incoming link to the origin node. Similarly, for case 4, this difference will be equal to minus 1 because for a destination node there will be no outgoing link, however there will be one exactly incoming link for which XA will be equal to 1, and therefore we can put together the optimization formulation for the shortest path problem as follows. So, we have this minimization of summation TA XA where the summation is going over all of the links in this set capital A, and then we have these two set of constraints. So, the objective function minimizes the total travel time for a path from node R to node S. The first set of constraints is the path connectivity constraint. So, as we had discussed, if we have a particular node that is not part of the shortest path or it is part of the shortest path, but it is neither origin nor the destination, then this difference of these two summations is equal to 0, and this difference is equal to 1 if it is the origin node and it is equal to minus 1 if it is the destination node. And then we have the definitional constraints here which are saying that XA will take binary values only, either 0 or 1. So, let us look at another important optimization formulation. This is a sensor problem. So, here we have endpoints given to us and there are two types of sensors, costly and cheap, that need to be placed at these points. The price of a costly sensor is denoted by C and that of a cheap sensor is denoted by C dash. And we are also given that there is a maximum budget for placing these sensors denoted by small b. And it is being assumed that at most one sensor of each type will be placed at any point. So, the question is how to place the sensor so that the number of points where at least one sensor is placed is maximized. So, one of the decision variables will be defined to be XA, which will be binary decision variable. It will take the value 1 if a costly sensor is placed at point A and 0 otherwise. Similarly, let us define another decision variable YA which is also binary. So, it will be equal to 1 if a cheap sensor is placed at point A and it will take the value 0 otherwise. And therefore, the budget constraint can be defined as follows. So, we are summing over all of the points capital N here. So, if a cheap sensor is placed at a point A, then Xa will be equal to 1 and it will have the contribution in this summation here, whereas if a costly sensor is placed, then Ya will be equal to 1 and there will be contribution for that. And therefore, only if a particular kind of sensor is placed at a point, then only we will take into account this contribution, and this total sum should not exceed the small b, that is the budget that is given to us. Now, let us define another binary variable Za, and this will be equal to 1 if there is at least one type of sensor, either cheap or costly on point A, and 0 otherwise. So, mathematically what it means is that Za is equal to 1 when Xa plus Y is greater than or equal to 1 and 0 otherwise. Now, note that this definition of Za depends upon what values Xa and Ya will take, which themselves are the decision variables in this problem, and therefore we want to represent this definitional constraint for Za in a way so that it can be represented in form of equalities rather than having this when condition while defining Za, and therefore we have introduced this sensor problem. So, let us define two constraints to define the decision variable Za. So, let M be a sufficiently large positive constant. So, in this example, the any value of capital M which is larger than or equal to 2 will work. So, the two constraints that define Za are as follows. This is the first constraint, that M times Za is greater than or equal to Xa plus Ya, and the second constraint is Xa plus Ya is greater than or equal to Za. Now, let us understand what do these constraints mean. So, the top constraint ensures that when Xa plus Ya is greater than or equal to 1, we have Za equal to 1, and the bottom constraint ensures that when Xa plus Ya is equal to 0, we have Z equal to 0. So, we can see that both of these two conditions are satisfied. So, for the top constraint, either Xa can be equal to 1, Ya can be equal to 1, or both can be equal to 1 if at least one of the sensors is placed at a point A. So, in the case when both Xa and Ya are equal to 1, so then Xa plus Ya will be equal to 2, and therefore we have placed this constant capital M along with Za so that this constraint can be satisfied, because Za can only take the value 0 or 1. So, if we had not placed this constant capital M together with Za, then inequality would not have hold, because then Za cannot take value 2, it can only go till value 1. And for this bottom constraint, it can be seen that when Xa and Ya are both 0, so then Za is restricted to be 0, there is no other choice. Now, note that there is another thing that needs to be ensured, that the top constraint should be such that it should allow Za to take value 0 when Xa plus Ya is equal to 0, and that does happen, although the value of Z equal to 1 will also be feasible, but we do not need to worry about that, because the bottom constraint will ensure that when Xa plus Ya is equal to 0, then Za has to be equal to 0, it will not allow Za to be 1. And similarly, the bottom constraint is such that it allows Za to take the value 1 when Xa plus Ya is greater than or equal to 1, although the value of Z equal to 0 will also work, but that is not a problem, because the top constraint ensures that when Xa plus Ya is greater than or equal to 1, we have Z equal to 1. So, this is the final formulation for the sensor problem. So, here we are maximizing the number of points where at least one kind of sensor is placed. So, therefore, we have this summation Za where A goes from 1 till capital N, and these are the constraints that we have. So, the first constraint ensures that the budget is satisfied. The next two constraints ensure that the variable Za is defined properly, and the last constraint is just saying that Xa, Ya and Za all are binary variables. So, now let us discuss some basic concepts or definitions related to optimization. So, let the decision variables be denoted by the vector x, and let us denote the objective function by the function zx. So, let the set of all decision variables which satisfy the constraints be capital X. So, capital X is called the feasible set or the feasible region. Now, a vector x that belongs to the set capital X is called a feasible solution, and a feasible solution X star is called a global minimum of this objective function Zx if Zx star is less than or equal to Zx for all feasible X. A feasible X star is called the global maximum of Zx if Zx star is greater than or equal to Zx for all feasible X. And a global minimum for the minimization problem or the global maximum for a maximization problem, they are all called optimal solutions. So, the shortest path problem that we had discussed was a minimization problem, because there we were interested in finding the path that had the shortest length, whereas fence and the sensor problems are examples of maximization problems. So, let us just see a quick example of an optimization formulation to understand this notation that was just introduced. So, consider that we are minimizing this function z, which is function of x plus y, such that x plus y is less than or equal to 2, x is greater than or equal to 0 and y is greater than or equal to 0. So, let us plot this, the feasible region for this optimization problem. So, since there are two decision variables, we have denoted them on the two axes that we have here. So, this is the origin here, this is the line x plus y equal to 2. Now, the feasible region will be such that it satisfies all of the three constraints. So, the first constraint says that x plus y is less than or equal to 2. So, this means that we have to be on this side of the line here, and the last two constraints say that we have to be in this first quadrant here, and therefore, the feasible region will be denoted by this shaded portion. This triangle denotes the feasible region. So, this is the set capital X, okay, and any solution that lies in this triangle is a feasible set or a feasible solution. Now, since we are interested in minimizing x plus y here, the optimal solution will be at the origin here 0 comma 0, because we will be getting the value of 0 plus 0 here. Now, let us discuss some important propositions here. So, if the feasible set is capital X, the solution x star is a global maximum of z if and only if x star is a global minimum of minus z for the same feasible set. So, since there is an if and only if condition here, let us prove this proposition from both the directions. We first argue that the first argument implies the second. Let us assume that x star is the global maximum of z on the set capital X. Then zx star is greater than or equal to zx for all x that lie in the feasible region. Now, if you multiply by minus 1 on both the sides here, then we will get minus zx star is less than or equal to minus zx, and therefore, x star is a global minimum of minus z. Let us now argue this, that the second argument implies the first one. So, let us assume that x star is a global minimum of the function minus z. Then minus zx star will be less than or equal to minus zx. Now, again multiplying by both the sides by minus 1 will give us that zx star is greater than or equal to zx, and therefore, x star is the global maximum of the function f on the set capital X. Let us look at another useful proposition here. Let x star be an optimal solution when the objective function is zx and the feasible set is capital X. Then for any constant b not depending on x, x star is also an optimal solution when the objective function is zx plus b and the feasible set is capital X. So, this proposition is saying that if you add a constant to the objective function, then the optimal solution does not change. And why is this useful? Because if you have a complex objective function and then if you have some constant present there, you can ignore the constants and solve that optimization formulation, and whatever optimal solution you get will be the optimal solution for the origin problem also. However, the optimal value of the objective function needs to be calculated while taking into account the original objective function. So, in that you need to take into account that there were some constants that were present. So, let us see how we can prove this. So, for this also we will go along the similar lines. So, without loss of generality, let us assume that the optimization problem is a minimization problem and that x star is the global minimum. Thus, zx star is less than or equal to zx for all x in the set in the set capital X. Therefore, b plus zx star is less than or equal to b plus zx for all x in the set feasible x. Thus, x star is also a global minimum and thus optimal when the objective function is zx plus b. So, this completes the result here. Okay. Now, there is another useful proposition. Let x star be an optimal solution when the objective function is fx and the feasible set is capital X. Then for any constant c which is positive, not depending on the decision variables, x star is also an optimal solution when the objective function is cfx and the feasible set is capital X. So, this proposition is saying that if you multiply the objective function by a positive constant, then the optimal solution does not change. So, this is also useful in the sense that you can throw away any positive constants while solving an optimization problem. For example, minimizing a function 100x will give the same optimal solution even if you just optimize the function x. So, this can also be proved in a similar way as the previous proposition. So, we will not discuss it here and we will leave it as an exercise. So, let us continue stating some of the important properties and concepts of optimization. The simplest optimization type that anyone will encounter is called linear optimization or linear programming. So, in linear programming, the objective function and constraints are linear. Now, every linear program, or in short LP, can be expressed in the following standard form. Now, this is the standard form. So, this is minimizing the summation Ci xi, where we have capital I decision variables and Ci is a constant, subject to the constraint that summation hij xi is equal to bj, where we have capital J such constraints, and note that hij, bj are all constants here, and we have the last set of constraints that xi is greater than or equal to 0 for all the decision variables capital I. So, you can see that the objective function summation Ci xi is first of all linear. The second set of constraints is also linear as they are linear equalities, and the last set of constraints is also linear as they are linear inequalities. Now, the following tricks can be used to convert any linear program in the standard form. So, for example, if we have a constraint of this type summation hij xi less than or equal to bj, so we can convert this into the form of constraints that were shown in the standard form by introducing a new slack variable x capital I plus 1 such that the summation hij xi plus xi plus 1 is equal to bj, and we put this additional constraint that x I plus 1 is greater than or equal to 0. So, you can see that this is equivalent to this original constraint that we have here. Similarly, if we have this constraint of the type summation hij xi is greater than or equal to bj, so this again can be converted into the standard form by doing a similar exercise. Now, in this case, we can again add a non-negative slack variable xi plus 1, but now we will be adding this on the right hand side. Now, suppose a variable xi is not constrained to be non-negative in the original problem. So, then how do we bring it in the standard form? So, for that we can introduce a new pair of non-negative decision variables xi plus and xi minus, and then what we can do is that we substitute xi equal to xi plus minus xi minus throughout the problem. Now, you can see that since these are non-negative decision variables xi plus and xi minus, so as such they do not put any restriction on the original decision variable that we had xi. And the important question is why the standard form is useful. It is useful sometimes in some algorithms such as simplex algorithm. Now, because of the time restriction, we will not be going into the details of the simplex algorithm, but another very important reason to know about the standard form is that it kind of serves as a check whether the given optimization formulation is linear or not. So, any linear program should be possible to convert into the standard form that we have given here. Note that the feasible region of all the linear programs can be graphed as a polygon if we have just 2 dimensions, that is, we just have 2 decision variables, and if there are more decision variables, for example, if there are 3 decision variables, then it will be polyhedron. Similarly, if we have even higher dimensions, then it will be polytope. So, in the figure shown here, we have this blue region which is denoting an example of a feasible region here. So these different kind of lines, you can think of them as different constraints here, and the intersection of all of these constraints is representing this feasible region blue. Now, since the two dimensions are already occupied by the two decision variables here in this case, so if we have to plot a function z, which is the objective function, and that itself is a function of these two decision variables, then either we need to have a z axis which is coming out, or we can plot it in this 2D itself by having these different contours here which are shown by the dashed lines. Now, for example, what can happen is that the lowest dashed line here can be thought of as having the value say 22, where all the points on this dashed line have value 22. Similarly, this line can be having all the values to be value 20, then 18, then 16 and so on. So this is a way you can represent the objective function value also in this 2D representation. So an important result that comes with the linear programming is related to extreme points or the corner points. So before we discuss that, let us discuss what an extreme point is. So an extreme point is a point which cannot be in the interior of any feasible line segment. So for example, these points C and D are extreme points, but A and B are not. Why A and B are not? Because they are lying in fact in the interior of the feasible line segment. So here you can see that point A is lying in the middle of this line segment shown here. Similarly, point B, although it is on this edge here, but still it is lying in the interior of this edge here. And these extreme points play an important role in the LP due to the following result. If a linear program has a global optimal solution and the feasible region has an extreme point, at least one of the extreme points is globally optimal. So this is a very strong result. So it is saying that if a global optimal solution exists and the feasible region has an extreme point, at least one of the extreme points will be having that optimal solution. So then you do not need to look at the interior of the feasible region. Now it can still happen that some of the optimal solutions are in the interior of this feasible region, but it is guaranteed that one of the optimal solutions will be at these extreme points or the corner points. And since all of these optimal solutions will have the same objective function value, as long as we are able to find one optimal solution, we are good. Thus, if one computes the objective function value at all the extreme points, one can determine the optimal solution, or in bracket globally optimal solution. Now in this course, whenever we talk about optimal solution, it automatically means globally optimal solution only. There is something called locally optimal solution that we will discuss later, but whenever we say it is an optimal solution, it in fact means it is the globally optimal solution. Now a simplex algorithm is an efficient way of searching these kind of extreme points for linear programs. Due to the time restrictions, we will not be discussing that algorithm, but the principle behind this is that there will be at least one corner points or the extreme points where there will be optimal solution. Now this result rests on this condition that the LP should be feasible, the linear program should be feasible, and the linear program should be bounded. So if these conditions are not met, then globally optimal solution may not be present. For example, consider this linear program which is maximizing 2x plus y, but we have the constraints x greater than or equal to 4 and x less than or equal to 2. So in this case, there is no feasible solution here, because there is no such x which is also greater than or equal to 4, but then also less than or equal to 2. Similarly, consider this linear program maximize 2x plus y such that x comma y is greater than or equal to 0. Now there is no bound to this objective function here, because as you keep increasing x and y, this objective function will increase, and since this feasible region is unbounded, so therefore this result that we said that the optimal solution will lie at one of the extreme points does not hold. But when the LP is feasible and the linear program is bounded, then the result that we discussed will work. So the fence problem that we discussed is not a linear program, because the objective function here is not linear, because it is L times W. The sensor problem and the shortest path problem are also not linear programs, because the decision variables are restricted to be integers there. So, in linear programs, the decision variables have to be continuous. So, in the next class, we will discuss additional optimization formulations for important problems. Thank you.